Noche Cósmica.
On a winter night in 1933, a Swiss astronomer named Fritz Zwicky stood before a telescope in California and made an observation that would quietly reshape everything we thought we knew about the universe. He wasn't looking for anything in particular. He was simply studying a distant cluster of galaxies, watching how they moved through the void, when he noticed something peculiar. The galaxies were moving far too quickly. They ought to have flown apart like scattered sparks, freed from the cluster by their own velocity, and yet they remained bound together, held by some invisible force. Zwicky did the mathematics and concluded that the universe must contain at least 400 times more matter than we could actually see. He called it dark matter, and in that moment, without fanfare or ceremony, he had opened a door that science has been gently pushing through ever since. If you find yourself drifting off to quiet, detailed stories like this one, take a moment to subscribe. It is the simplest way to make sure the next long journey through the story of most relaxing facts about dark matter finds its way back to you. If you have ever felt the pull of a mystery that doesn't demand an answer, but simply invites contemplation, consider following along as we explore the most relaxing facts about dark matter, those quiet, patient discoveries that reveal how much of the cosmos remains hidden, unseen, and somehow deeply calming to consider. You'll find each fact unfolds like a slowly deepening breath. Begin with the night sky itself. Step outside, and you will see starlight, that ancient radiation traveling toward you across impossible distances. Those pinpricks of brightness are what we know. They are the visible scaffolding of creation. But here is what the darkness between them contains. Here is what makes the night so much more than what appears. Around those stars and galaxies and clusters drifts something far more abundant, far more patient, far more fundamental than anything that glows. This invisible substance makes up roughly 85% of all the matter in the universe. We call it dark matter, and we cannot see it, cannot touch it, cannot measure it directly. And yet we know it is there. We know it with the same certainty we know the wind exists, not by looking at it, but by watching how it bends the trees. The quiet beauty of dark matter lies in this paradox. The universe is fundamentally shaped by something we cannot perceive directly. Galaxies spin and swirl and maintain their form only because of dark matter's gentle gravitational pull. Galaxy clusters remain bound together across the cosmic void because of its invisible presence. The very structure of the cosmos, the great filaments and voids that give space its architecture, the cosmic web that connects all things, exists because dark matter provided the foundational scaffolding upon which ordinary matter could gather, condense, and form stars, planets, and eventually, observers capable of wondering about their own origin. Think of it this way. If you have ever listened to a piece of music and been moved by the silence between the notes, you understand something of dark matter's role in the universe. The silence is not nothing. It is the space that gives the notes their meaning. Without the darkness, without the space, without the emptiness, the notes would lose their power. The universe works in much the same way. The visible matter, the stars, the gas, the dust, the planets, is like those notes. But the cosmic music could not exist without the vast, invisible silence of dark matter surrounding everything, shaping everything, holding everything together through the patient, eternal pull of gravity. On that winter night when Zwicky made his discovery, he was observing something that had been true since the first moments after the Big Bang itself. Dark matter had always been there. It had always been the dominant form of matter in the universe. Humans simply had not yet realized it. For thousands of years, we looked up at the night sky and saw only light, and thought we were seeing everything. We were seeing less than 1/6 of what was actually there. The other 5/6 drifted silently around us, shaping the cosmos according to laws we were only beginning to glimpse. What is remarkable about dark matter is how calm it seems, how patient. It does not rage, it does not burn, it does not create light or heat or any signal we can detect with our ordinary senses. It simply exists, and through the quiet persistence of gravity, it shapes the entire architecture of reality. There is something profoundly restful in that. There is something deeply soothing about contemplating a universe in which the vast majority of what exists operates in silence, works according to laws that are elegant and patient and utterly indifferent to human anxiety. And as you sit here in the darkness, it is worth reflecting. This darkness you are in, this silence around you, this quiet night, it is not empty. The dark matter passes through the room where you are right now. It is passing through your body. It has been moving through the cosmos since the universe began, and it will continue moving long after everything we know has faded away. It connects you, in a physical sense, to every star that has ever burned and every galaxy that has ever spun. The same invisible architecture that holds the universe together holds you in place. This is what makes the universe feel less like a machine and more like something alive with meaning, even in its silence, even in its darkness, especially in its darkness. If you find yourself drawn to the quiet corners of existence, to the parts of the world that sit just beyond the reach of our instruments and our understanding, then there is something in the very structure of this mystery that invites a deeper knowing. Dark matter is not the sort of cosmic puzzle that demands immediate answers or urgent resolution. It is, instead, a patient teacher, a guide into the slower rhythms of how science actually unfolds, how knowledge builds itself grain by grain across the decades. And if you would like to follow this gentle unraveling deeper into the night, to discover how physicists have learned to listen for the whisper of invisible mass, to understand the strange logic by which we know something exists precisely because we cannot see it, then do consider subscribing to the channel. With each episode, we move further into the shadows, where the universe's deepest structures hide in plain sight, where the answers we seek are already here, waiting for us to learn the language in which they speak. There is a peculiar comfort in this sort of inquiry, in following a thread that does not immediately resolve, but rather opens into wider and wider chambers of wonder, each one as calm and spacious as the last. The story that unfolds across the coming hours traces the journey of human perception, learning to recognize absence as presence, learning to see what is not there by observing what it does. It is a journey that begins in the quietest possible way, with astronomers noticing something strange in their observations, a small inconsistency that would not go away no matter how carefully they checked their instruments. And as we move through this landscape together, through the work of patient observers and careful theorists, through laboratories buried deep beneath the Earth and satellites circling the globe, you will discover that the pursuit of dark matter is not really a pursuit at all. It is more like a conversation with the universe conducted in a very slow language, one word per decade, one measurement per generation. There is nothing hurried about it. There is nothing that demands your vigilance or your worry. And so, as we continue deeper into this vast and tranquil mystery, allow your mind to settle into the same patient rhythm that has carried cosmology forward. Allow yourself to become curious in the way that only a restful mind can be curious, without urgency, without strain, simply wondering. The darkness that surrounds us, both in the night sky above and in the cosmic distances beyond, is not empty. We know this now, though it took the better part of a century for science to articulate what that knowing means. The darkness is full. It is dense with presence. And yet the presence is so gentle, so perfectly invisible, that we might never have noticed it at all, were it not for the way it moves, were it not for the way it guides galaxies in their long, patient journeys through space, were it not for the way it bends light itself around its invisible form. For much of human history, we saw only the luminous things, the stars, the galaxies burning like embers in the night. And this was enough. This was the universe we could touch, the universe we could understand. But in the 20th century, as our instruments grew more sensitive and our theories more refined, we began to notice something peculiar. We began to notice that the luminous universe, all the stars and gas and dust we could actually see, was only a tiny fraction of the story. The real universe, it seemed, was mostly dark, mostly hidden, mostly speaking to us through its effects rather than through any light of its own. And this realization, which might have seemed unsettling to an earlier generation, begins to feel almost restful when you sit with it long enough. There is something deeply calming about the idea that most of the cosmos is gentle and invisible, that most of existence unfolds according to laws that do not need the glare and noise of starlight to be true. The darkness is patient. The darkness is vast. The darkness is where the real architecture of the universe is written, in a language of gravity and mathematics, in the slow choreography of mass-bending space and time around itself. To follow this mystery deeper is to learn to be comfortable with unknowing, to learn to find peace in questions that may not have answers for generations yet, to discover that some of the most important truths about reality are precisely those that do not announce themselves with light and sound, but rather whisper their presence through subtle effects, through the bending of a galaxy's rotation, through the way light curves around an invisible lens, through the patient accumulation of evidence that something vast and intelligent and utterly silent is there, holding everything in place. This is an invitation to think differently about what knowledge means. Not all understanding comes from seeing with your eyes. Not all truth announces itself loudly. Some of the deepest truths about the structure of existence reveal themselves only to those patient enough to listen for the silence underneath the noise, to notice the ways in which matter and energy move in patterns that suggest a hidden choreographer. And that choreographer, that vast, invisible presence that shapes everything from the spinning of galaxies to the large-scale structure of the universe itself, is what we call dark matter. We do not yet know its name, in a deeper sense. We do not yet know what it is made of, but we have learned its language. We have learned to read its signature in the motions of the cosmos. And as we go deeper into this mystery together, you will discover that this language is perhaps the most soothing language the universe speaks, a language of patience, of waiting, of trusting that the answers will come, in time, to those who listen well enough. When astronomers and physicists speak of dark matter, they are describing something genuinely peculiar, substance that exists all around us, throughout the cosmos, yet leaves no light, absorbs no light, and emits no light whatsoever. It is matter that speaks only in the language of gravity. It pulls, it binds, it shapes. Yet it remains forever silent and invisible to every telescope humanity has ever built, whether those telescopes peer in visible light, infrared, ultraviolet, radio waves, or X-rays. There is something almost meditative about this invisibility, isn't there? An entire ocean of material drifting through the universe, patient and unobtrusive, doing the quiet work of holding galaxies together while asking nothing in return, not even to be seen. For much of human history, we didn't know it was there at all. The night sky seemed to contain everything we needed to understand, stars and nebulae and the slow march of planets across the heavens. But as our instruments grew more precise, and as we learned to measure the motions of galaxies with increasing accuracy, a strange discrepancy began to emerge. Galaxies were moving in ways that the visible matter alone could not explain. They spun too quickly. They clustered together with too much force. Something invisible was present, something with mass, something with gravity. And this something seemed to comprise more of the universe than all the stars, planets, gas clouds, and light-emitting matter combined. We live, it appears, in a universe that is mostly dark. The term itself, dark matter, is beautifully honest in its simplicity. It does not attempt to describe what the substance is. It describes only what it is not. It is not radiating light. In this way, the name carries within it an acknowledgement of human limitation. We have named it not for what we know about it, but for what we do not know. There is something restful in this humility, something almost Buddhist in its acceptance of mystery. Science proceeds not by pretending to have all the answers, but by naming precisely what it does not yet understand, then sitting patiently with that unknowing, while the evidence slowly accumulates. And dark matter has proven itself to be remarkably patient. For nearly a century now, nearly 100 years, scientists have known that this invisible substance exists, and yet its fundamental nature remains undetermined. This is not a failure. Rather, it is one of the greatest ongoing mysteries in science. And mysteries, when examined closely, are often deeply soothing. They remind us that the universe does not yield its secrets quickly. They ask us to slow down. They ask us to observe. They ask us to sit with questions for decades or centuries if necessary, building evidence gradually, carefully, without rushing toward false certainty. Consider the contrast with other great scientific mysteries that have since been solved. When scientists wondered about the nature of atoms, or the source of the sun's energy, or the mechanism of heredity, those mysteries eventually gave way to elegant answers. But dark matter has resisted all attempts at quick resolution. It has become something different, not a problem to be solved in a decade, but a companion mystery that we have learned to live alongside. In this way, it resembles the night sky itself, a presence so vast and constant that it becomes almost invisible through familiarity, yet always there, always patient, always inviting deeper observation. What dark matter does, with absolute certainty, is gravitationally influence everything around it. We can see its effects the way we can see the wind's effects on trees without ever seeing the wind itself. We measure its presence through gravitational lensing, the bending of light around massive objects, the way one might infer an invisible boulder in a river by watching how the current flows around it. We detect its fingerprints in the large-scale structure of the universe, in the way galaxies cluster and filaments of matter stretch across billions of light years. We read its signature in the ancient light of the cosmic microwave background, that gentle radiation echo of the universe's infancy. And through all these indirect observations, we have learned that dark matter comprises roughly 27% of the universe's total matter-energy content. The remaining 73% is dark energy, an even deeper mystery. But our focus here rests with the dark matter, this quieter, more gravitationally knowable form of cosmic darkness. What is peculiar and strangely comforting about dark matter is how little it seems to disturb the universe's peace. It does not collide. It does not create bright explosions or violent reactions. Unlike ordinary matter, the stuff of stars and planets and your own body, dark matter passes through ordinary matter with barely a whisper. Two dark matter particles might travel through the same cubic centimeter of space for billions of years without ever touching, without ever interacting at all. They are like invisible ghosts drifting through a mansion, present but untouchable, affecting only through the gentle, constant pull of gravity. In this way, dark matter has given the universe an elegant simplicity. It shaped galaxies and clusters without the chaotic drama that ordinary matter requires. It provides the scaffold. Ordinary matter decorates it. Light and violence and life dance upon the structure that dark matter so quietly provides. This is why dark matter, despite its essential role in our cosmic story, feels like one of the calmest subjects in all of physics. There are no explosions here, no sudden transformations, no dramatic collapses. There is only the slow and patient accumulation of more and more evidence that something vast and invisible surrounds us, has always surrounded us, and will continue surrounding us whether we ever fully understand it or not. The universe did not require our understanding to function perfectly well. It got along invisibly for billions of years before we noticed it was there, and it will continue getting along perfectly well, drawing galaxies together, shaping the cosmic web, maintaining the large-scale structure of all existence, in the same unhurried, unnoticed manner it always has. The story of dark matter truly begins in the quiet observatories of the 1930s, when astronomers began noticing something that didn't quite fit. Picture, if you will, a Dutch astronomer named Jan Oort, sitting with his calculations late into the evening, studying the motions of stars within our own galaxy, the Milky Way. He was watching how these stars orbit around the galactic center, much as planets orbit the sun, and he began to see something that troubled him in the gentlest possible way. The stars were moving too quickly, all of them. They were circling the galactic heart, with velocities that should have flung them out into the void, like riders flying from a too fast carousel, and yet they remained, held in place by gravity that the visible matter alone could not possibly provide. It was as though someone had invited guests to dance in a vast ballroom, and the music was far more powerful than any orchestra he could see. Oort did not immediately leap to the conclusion that invisible matter existed. Instead, he sat with the question. He wondered if perhaps his measurements were somehow off, if the light years and parsecs he was calculating had deceived him. But the numbers persisted, calm and patient, refusing to be explained away by simple error. And so he began to voice a quiet possibility, that the galaxy must contain far more matter than what we could see, matter that produced no light, matter that revealed itself only through the gravitational tug it exerted on the visible stars. He called this invisible substance dark matter, a term both humble and precise, acknowledging simply that it was matter we could not see. Around that same time, across the ocean in California, another astronomer named Fritz Zwicky was making similar observations, though his were on a vastly grander scale. Zwicky was studying not individual galaxies, but entire clusters of galaxies, vast congregations of light islands separated from one another by the darkness of space. He was calculating the velocities of these galaxies as they moved through their clusters, watching how they orbited around common centers of mass. And here, too, he found the same gentle impossibility. The galaxies were moving far too rapidly to be held together by the gravitational attraction of all the visible light he could measure. The clusters should have been torn apart long ago, each galaxy flying off into the cosmic darkness, and yet they remained, bound together as if by invisible threads, as if held in the patient embrace of something unseen. What strikes us now, listening to this story unfold across the decades, is how peacefully these discoveries were made. There were no dramatic moments, no sudden revelations beneath thunder and lightning. Instead, there were careful measurements, thoughtful calculations, and the slow realization that the universe was far richer and far more mysterious than the light alone could tell us. Zwicky, like Oort, began to speak of this unseen substance with a kind of wondering acceptance. He called it dark matter as well, and he estimated, with remarkable prescience, that this invisible material made up the vast majority of the universe's mass. Think of it. Nearly a century ago, scientists were suggesting that everything we could see, every star, every planet, every speck of dust illuminated by light, comprised only a small fraction of what actually existed in the cosmos. The word dark in this context carries no sinister meaning. It simply means that this matter does not emit or absorb light in any significant way. It is not black, in the way that a black hole appears black because its gravity traps light. It is simply silent. It interacts with the visible universe only through gravity, the most patient and pervasive of forces, the one that works its influence across the vast distances of space, asking nothing in return, expecting no acknowledgement. And in that silence, there is something almost restful about it, a mystery that does not demand immediate resolution, a secret that the universe has been quietly keeping all along. The 1930s discovery was not met with fanfare or immediate acceptance. Many astronomers remained skeptical. Could the calculations be wrong? Could there be errors in the distance measurements, in the redshift observations that told them how fast galaxies were moving? Could it be that our understanding of gravity itself was somehow incomplete? These were reasonable questions, and they were asked gently, without the adversarial tone that sometimes characterizes scientific disagreement. The idea of dark matter settled into the community of astronomers like a visitor who arrives quietly, without announcement, and gradually becomes so familiar that one forgets what the house was like before they came. Oort and Zwicky had planted a seed, and though it would take decades, indeed, it would take the work of another remarkable astronomer half a century later, before that seed would truly flourish, the foundation had been laid. The universe had revealed, in the most patient way imaginable, that it contained vastly more than met the eye. There is something profoundly calming in contemplating this moment in the history of science. Here were astronomers, armed with nothing but telescopes, patient observation, and mathematical reasoning, discovering that they lived in a cosmos far more vast and far more mysterious than they had supposed. And instead of despair or frustration at this ignorance, there was instead a kind of wonder, an openness to the possibility that the universe was teaching them something, showing them that there was far more to learn, far more to discover, far more to understand about the deep architecture of reality. The unseen hands that guided the galaxies were gentle hands, and they were inviting humanity to understand them, one careful measurement, one thoughtful calculation at a time. By the middle of the 20th century, something curious was happening in the quiet observatories where astronomers watched the slow pirouette of distant galaxies. The hints that Oort and Zwicky had noticed decades before, those galaxies behaving as though invisible hands were guiding them, had begun to feel less like oddities and more like an invitation to look deeper. But it took a particular kind of patience and a particular kind of attention to hear what the universe was trying to say. In the 1960s, a woman named Vera Rubin sat in the dome of the Lowell Observatory in Arizona, her eye pressed to an instrument that would change how we understood the cosmos. Beside her worked Kent Ford, a quiet engineer whose innovations in measuring the light from distant worlds would prove as crucial as her own curiosity. They were observing something deceptively simple, the way galaxies spin. How fast do the outer edges of a galaxy move as it rotates? The answer, according to every expectation, should have been straightforward. Stars farther from the galactic center, like planets farther from the sun, should move more slowly. The mathematics was old, proven, inevitable. And yet, when Rubin and Ford gathered their measurements, year after year, galaxy after galaxy, they found something that shouldn't have been there. The outer edges of galaxies were moving just as fast as the inner regions. Imagine a phonograph record where the outer grooves spin at the same speed as the center. It defies the gravity we thought we knew. It seemed to violate the very laws that keep planets in their orbits and hold moons in their graceful dance. But the measurements were precise. The observations were patient and repeated. The universe, it seemed, was not following the script. This discovery, which Rubin would spend decades refining and publishing and sharing with a scientific community that was, at first, reluctant to believe her, pointed toward a stunning conclusion. If the outer regions of a galaxy were moving too quickly to be held by the visible matter alone, by the stars and gas and dust that we could actually see through our telescopes, then there had to be more mass there, much more. Mass that cast no light, mass that reflected no starlight, mass that was, quite simply, invisible. The revelation arrived not with drama, but with a kind of gentle inevitability. Here was the evidence, patient and unmistakable. Galaxies were not spinning the way they should. They were spinning the way they would spin if they were wrapped in a halo of invisible material, a diffuse cloud of something unknown that extended far beyond the visible galactic disk. This unseen material comprised perhaps 5 or 6 times more mass than all the stars combined. It was there. It was real. It was patient, as dark matter would turn out to be patient in all its dealings with us. What made Rubin's work so profound was not just that she found the evidence. It was that she found it for galaxy after galaxy after galaxy. This was not an anomaly. This was not a single puzzling case. This was the rule. From spiral galaxies in nearby space to those wheeling in the distant reaches, the same pattern emerged. Every galaxy seemed cloaked in this invisible mantle. Every galaxy was held together, made stable, made coherent by matter that had no voice, cast no shadow, announced itself only through the mathematics of gravity. The 1970s saw these observations accumulate like snow gathering on a winter landscape. Rubin's careful, methodical work began to shift the thinking of the entire field. Here was something undeniable, something that repeated itself across the observable universe. The inner regions of galaxies could not account for their own rotation. There was missing mass, and it was everywhere. Not just in one galaxy, not just in one cluster. It was a feature of the cosmos itself. It was, in a sense, the foundation upon which all visible galaxies rested. There was something almost meditative about the way this discovery unfolded. It did not arrive as a shock. It arrived as a series of careful observations, each one adding a brushstroke to a slowly emerging picture. Rubin herself would spend 40 years exploring these rotation curves, publishing hundreds of papers, becoming one of the most respected voices in astronomy, though recognition came more slowly than her science deserved, and that patient injustice was part of her story too. But the work itself was quiet, methodical, and utterly compelling. Here was the universe speaking in the language of light and gravity, and someone was finally listening closely enough to hear it. The implications began to settle into the consciousness of astronomers like Autumn Frost. If galaxies were surrounded by these invisible halos, then the universe was not at all what we had imagined. It was not a collection of isolated islands of light in an empty sea of darkness. It was something far more interconnected, far more structured, far more alive with invisible architecture. The dark matter was not incidental. It was not a minor correction to our calculations. It was fundamental. It was primary. It was, in fact, the dominant structure around which all visible matter gathered. And yet, in those 1970s observatories, in those patient nights of measurement and analysis, there was no sense of crisis or panic. There was simply a deepening of mystery, a widening of wonder. The universe, it seemed, had secrets. It had hidden dimensions. It had a quiet way of revealing itself only to those patient enough to listen, careful enough to measure twice, brave enough to report what the numbers actually said, even when it contradicted everything that had come before. Now, before we venture much further into this quiet landscape of invisible matter, it helps to pause and consider what dark matter is decidedly not. And this distinction, this careful sifting of possibilities, is where the science becomes something almost meditative in its patience. The first and most common misconception that drifts through public conversation is the idea that dark matter might simply be black holes. It's an understandable confusion. Black holes are dark, after all. They consume light. They are genuinely difficult to detect, and for many decades physicists wondered whether the missing mass in galaxies could be explained by a population of black holes we simply hadn't found yet. But here is where the numbers begin to tell a gentler, more nuanced story. To account for all the gravitational effects we observe, the way galaxies rotate, the way clusters hold together, the way light bends around massive structures in space, we would need an almost impossibly vast quantity of black holes. Not just a few here and there, but so many that the universe would be crowded with them, constantly merging, constantly emitting radiation that we would have detected by now. The universe, in other words, would be far more violent and luminous than it actually is. And yet it remains, in most places, a quiet expanse. The gentle hum of the cosmic microwave background is almost the only whisper we hear from the epoch of the early universe. Black holes cannot explain the dark matter we're seeking, not without painting a picture of the cosmos that contradicts nearly everything we observe. What about ordinary dust and gas? Surely, one might wonder, the missing mass could simply be vast clouds of cold gas and dust, the kind that drifts between stars and occasionally condenses into new suns. This too seems plausible on the surface. After all, we know cold gas exists. We see its effects. We study its chemistry. But here again, the data guides us toward a different conclusion. If dark matter were made primarily of cold gas or dust, we would expect to see its signature in the light that passes through it. Gas absorbs light at particular wavelengths, it reddening distant starlight in characteristic ways. Dust scatters and obscures. When astronomers pointed their instruments at the regions where dark matter should be densest, in the halos around galaxies, in the vast filaments stretching between galaxy clusters, they found none of these telltale marks. The light arriving from distant quasars and galaxies behind these dark matter concentrations reached us unaltered, uninterrupted, as if nothing were there at all, even though gravity insisted that something decidedly was. And then there is the notion of dark stars, hypothetical objects, less luminous than ordinary stars but still composed of ordinary matter. Perhaps, the early thinking went, the halos of galaxies were filled with vast numbers of small, cool, invisible stars. Stars that had never ignited fusion. Stars that had cooled and darkened over billions of years. Some researchers even gave them a name, massive compact halo objects, or MACHOs, and embarked on searches to find them. The search was conducted with great ingenuity. Astronomers looked for gravitational lensing events, moments when a dark star's gravity would momentarily magnify the light of a distant star behind it. They found some, but not enough. Not remotely enough to account for the bulk of the missing mass. Moreover, we have other lines of evidence that would constrain how many such objects could possibly exist without violating what we know about the early universe, the formation of light elements, the way galaxies could have assembled themselves. Dark matter, it became increasingly clear, is not simply a collection of failed or dormant stars. It is not ordinary atoms that have simply gone cold and dark. It is something different, something altogether more exotic and strange. And perhaps that strangeness is part of what makes this mystery so peaceful to contemplate. For once we accept that dark matter is not what we initially expected, not what we can readily see or touch or directly detect through conventional means. We enter a realm where certainty gives way to elegant ambiguity. The universe, it seems, has hidden the bulk of its matter in a form we have not yet truly identified. And yet we can measure its effects with remarkable precision. We can map it, we can weigh it, we can trace its influence across billions of light years. This is the paradox that rests at the heart of modern cosmology. We know it is there, we know it matters profoundly, and we do not know what it is. There is something almost restful about that admission, something deeply scientific about the willingness to say, with quiet certainty, that we do not yet have the answer. Not every mystery in the cosmos needs to be rushed toward closure. Some mysteries are meant to be dwelt within, explored gently, approached with patience and wonder rather than urgency, and dark matter invites precisely that kind of slow, meditative inquiry. As we drift further into this exploration, then, let us carry with us this clarification. Dark matter is not what we see. It is not what we expect, and that very quality, that difference from our initial assumptions, has opened new ways of thinking about the universe itself. By the 1980s, something remarkable was happening in the quiet offices and computer labs of cosmologists around the world. The universe itself was beginning to reveal its hidden architecture, and dark matter had moved from being a curious footnote in astronomical observations to becoming something far more fundamental, an essential ingredient in understanding how everything came to be. These were the years when the invisible became indispensable, when scientists began to ask not merely whether dark matter existed, but how it had shaped the very first moments of cosmic time. Vera Rubin's galactic rotation curves had provided the observational bedrock. The spiraling motions of stars in distant galaxies could not be explained without invoking massive amounts of unseen matter surrounding them like invisible halos. But in the early 1980s, a new generation of theorists began to ask a deeper question. If galaxies were embedded in these halos of dark matter, what did that mean for the universe's earliest epoch, those first few 100,000 years after the Big Bang, when all the matter and energy in existence was compressed into something almost impossibly dense and hot? How had the seeds of galaxies formed in the first place? This is where the tapestry really begins to weave itself together. Computer simulations were becoming more sophisticated, more patient in their calculations. Researchers like George Blumenthal, Joel Primack, and others in California began to run calculations on early supercomputers, machines that would seem almost quaint by today's standards, yet possessed enough power to model the universe's growth across billions of years. These simulations ask the cosmos a gentle question. If you start with a universe containing ordinary matter, radiation, and dark matter in precisely the proportions that observations suggested, what structures would naturally emerge as that universe expanded and cooled? The answer was not obvious. In fact, it was beautiful. Without dark matter, the simulations suggested, galaxies simply could not form. Here is why. In the earliest universe, matter was nearly perfectly uniform, just slightly denser in some places than others. Ordinary matter alone would have moved too slowly under its own gravity to gather these tiny density variations into the magnificent structures we see today. But dark matter was different. Dark matter particles, barely interacting with light or ordinary matter, could begin gravitating together from the very earliest moments. They could accumulate in clumps, building gravitational wells into which ordinary matter would eventually fall and collapse into galaxies and galaxy clusters. Dark matter, in other words, was not a passenger in cosmic history. It was the driver. The elegance of this realization unfolded slowly through the decade. Researchers published paper after paper, each one adding another thread to the growing tapestry. What emerged was this: the universe's large-scale structure, the vast cosmic web with its galaxy filaments and enormous voids, had been sculpted primarily by dark matter. Galaxies had formed along the densest strands of the dark matter network, like beads threaded onto invisible cosmic strings. The architecture of the universe on the grandest scales was fundamentally determined by something we could not see, could barely measure, and could not yet identify. There was something deeply restful about this idea, once one sat with it for a while. It suggested that the universe operated according to principles both simple and profound. The laws of gravity, unchanged since Newton first described them, were sufficient to explain the cosmic structure. Dark matter was not magical. It was simply matter, ordinary, comprehensible matter that happened to be invisible. The universe was not more complicated for this revelation. It was, in a strange way, more coherent. The physics fit together more elegantly. By the mid-1980s, The concept had become so established that it was beginning to reshape how cosmologists approached fundamental questions. If dark matter made up perhaps 85% of the matter in the universe, then ordinary matter, you and me, the Earth, the stars, all the things we could see, was truly the minority species in a dark matter-dominated cosmos. This was a profound reorientation. For centuries, astronomy had focused on light, on the visible. Now, scientists were realizing that the visible was merely the glowing surface of something far vaster, far deeper, far more substantial. And here is where the nighttime contemplation deepens even further. Think about what this means for your own place in the cosmos. Everything you have ever seen, every star, every galaxy, every cluster of galaxies stretching across billions of light years, represents only a small fraction of the actual matter that surrounds you. Around every visible galaxy spins a halo of dark matter, perhaps 10 times more massive than all the visible stars and gas combined. You are not standing on the dominant matter in the universe. You are standing on something rare, something exceptional, something that formed only because of the patient gravitational shepherding of invisible guides. The 1980s saw cosmologists beginning to weave dark matter into their mathematical models with increasing confidence, not because they had discovered what it was, but because it was the only way to make the mathematics of cosmic structure match what telescopes were actually showing them. The universe would not cooperate with models that left dark matter out. Galaxy clusters moved as they did because of dark matter. Galaxies rotated as they did because of dark matter. The patterns of the cosmic microwave background radiation, that ancient light from the Big Bang itself, could only be explained if dark matter played a fundamental role in how the universe expanded and evolved. This is the period when dark matter transformed from being a peculiar puzzle into being the foundation of our understanding of the cosmos. It happened not with a dramatic discovery, not with a eureka moment, but gradually, patiently, as simulations grew more sophisticated and observations accumulated. Theory and observation began to converge, like two solitudes slowly discovering that they were describing the same thing. And as they did, a different kind of scientific beauty emerged. Not the beauty of certainty, but the beauty of coherence, of pieces fitting together, of mystery beginning to yield its secrets to patient inquiry. Picture, if you will, the universe not as a uniform soup of matter, but as something far more intricate, a vast network of filaments and walls, holding galaxies the way a spider's web holds dewdrops at dawn. This is the cosmic web, and it is perhaps the most patient, most beautiful architecture that dark matter has quietly constructed over billions of years. In the 1980s and into the 1990s, as computers grew powerful enough to simulate the universe itself, cosmologists began to see something remarkable emerging from their calculations. When they ran the math forward from the Big Bang, allowing gravity to work its slow, inexorable way on clumps of dark matter seeded through the early cosmos, the invisible matter did not spread evenly. Instead, it accumulated, pooled, accumulated more. Dark matter drew together into thin filaments, vast threads of invisible mass that stretched across hundreds of millions of light years. At the intersections where these filaments met, the density rose, and there the visible matter, the ordinary atoms and molecules we can see, gathered too. Galaxies formed along these threads. Galaxy clusters assembled at the junctions, and the cosmic web was born. Think of it as a kind of cosmic city planning, except the architects were gravity and time, and they worked without hurry or haste. The dark matter was there first, forming the scaffolding. Then galaxies clustered along those invisible supports like lights strung along a wire. The entire structure, every galaxy you have ever seen through a telescope, every cluster of billions of stars, the very way clusters bunch together into superclusters. All of it traces the underlying geography of dark matter's patient construction. What is perhaps most soothing about this image is that it is not chaotic. The cosmic web is ordered, structured, almost architectural in its elegance. There are filaments of dark matter, quiet and steady. There are nodes where filaments meet, where matter congregates. And there are vast voids, enormous empty spaces between the filaments where almost nothing dwells. These voids can stretch for 100 million light-years or more, and they are nearly empty, just a handful of galaxies drifting through cosmic emptiness. The contrast between the filaments and the voids creates a structure so large, so carefully balanced, that it feels less like accident and more like something that was always meant to be this way. How did astronomers first come to recognize this cosmic web? By mapping. In the 1980s and 1990s, surveys began to compile three-dimensional maps of the galaxy distribution in our universe. They would measure the distance to thousands, then tens of thousands, then hundreds of thousands of galaxies, plotting each one in space. And as the maps grew more detailed, the filamentary structure emerged like a drawing, revealed slowly in dim light. The walls became visible, the voids opened up. Astronomers realized they were not looking at random scatter, but at something deeply organized, deeply patterned. The cosmic web was not a theory, it was an observation. Some of the early surveys that revealed this structure had names that still carry a sense of quiet wonder. The Sloan Digital Sky Survey began its mapping work in 2000, systematically cataloging millions of galaxies and their positions. The 2-degree field galaxy redshift survey, before it had begun the hard work of measuring distances, building the three-dimensional map piece by piece. These were patient endeavors, methodical, precise. Thousands of nights of observation, each one a small contribution to a vast picture. And slowly, as the data accumulated, the cosmic web became undeniable. It was real, it was everywhere. The dark matter, invisible though it is, forms the backbone of this web. Its gravity is what pulled the filaments into shape. Its presence is what keeps the galaxies bound within those filaments, moving together in the slow dance of cosmic gravity. The visible matter, the stars, the gas clouds, the planets, is like decorative inlay on a framework of dark wood. 90% of the matter along these filaments is dark, unseen. Only 10% is the ordinary matter we can observe, and yet it is the dark matter that provides the structure, the support, the invisible architecture that holds it all together. There is something restful in contemplating this, is there not? The universe is not held up by visible forces alone. There is a hidden hand at work, patient and gentle, weaving matter into form across distances so vast that light itself takes millions of years to traverse them. This invisible scaffolding never advertises itself. It does not shine or radiate. It simply works, doing its job with the steady persistence of gravity itself. Within each filament, there is motion. Galaxies are not static along these threads. They orbit, they interact, they move toward the nodes of highest concentration. In time, and we are speaking of timescales of millions and billions of years, these motions bring galaxies together into clusters and superclusters. At the nodes, the collision is not violent on the scale we might imagine. Instead, it is more like a slow-motion merger, where galaxies gradually orbit closer to one another, their mutual gravity drawing them into ever tighter configurations. The dark matter of one galaxy begins to mingle with the dark matter of another. The structures blend, new, larger structures form, and the cosmic web continues to evolve, to thicken in some places, to thin in others, following the patient logic of gravity across billions of years. Consider also the cosmic voids, those vast empty spaces between the filaments. For a long time, astronomers wondered, are the voids truly empty, or is there some faint material within them that we simply cannot detect? The answer, it appears, is closer to truly empty than we might have guessed. The voids are regions where dark matter is sparse, where the cosmological story has produced fewer galaxies, less density. It is as if the cosmic web were a piece of lace, where the threads are real and substantial, but the spaces between them are genuinely open, genuinely sparse. There are galaxies in the voids, certainly. Some galaxies have found themselves, by chance, isolated between the great filaments. But they are far fewer and farther between. The voids are lonely places, calm places, where a solitary galaxy might drift for billions of years with few neighbors to interact with. This vision of the cosmic web, these filaments and nodes and voids, is not merely a pretty picture. It is also a powerful tool for understanding how the universe came to be as it is. The web is the stage upon which galaxy formation occurred. Without the filaments, galaxies would have had nowhere to cluster. Without the nodes, there would be no galaxy clusters, no great assemblies of thousands or tens of thousands of galaxies bound together by gravity. The cosmic web is the foundation of large-scale structure in the universe, and without dark matter, there would be no web at all. And yet, here is something to ponder as your mind drifts along these invisible threads. We have never seen the dark matter directly. We infer its presence from the way it shapes what we can see. It is like an architect whose blueprints are never revealed, whose name is never signed, but whose influence is visible in every structure built. The cosmic web exists because of dark matter's presence, and yet the dark matter itself remains hidden, patient, quiet, going about its slow work of holding the universe in shape for billions of years to come. And here is where the mathematics becomes almost physical, almost visible. Imagine yourself standing at the edge of a vast invisible presence, not hostile, but simply there, immense and patient. You cannot see it directly, but you can watch how light itself responds to it. This is gravitational lensing, and it is perhaps one of the most elegant demonstrations that dark matter truly does bend the fabric of space around itself. Light we think of as straight. It is the straightest thing we know. It travels through the vacuum at a constant speed, asking nothing of the universe except passage. And yet, and this has always been one of the quieter miracles of physics, light does not truly travel straight when it moves past a massive object. It curves. The mass warps space itself, and light, being obedient to the geometry of space, follows that curve. The more massive the object, the more pronounced the bending. The effect is subtle enough that it was only confirmed during a solar eclipse in 1919, when physicists could finally see stars whose light had curved around the sun's gravity, while the sun itself was hidden from view. Now extend that image. Imagine not the sun, but an entire galaxy cluster, millions of galaxies bundled together by gravity, their combined mass pressing down on space like a weight on silk. Most of that mass is dark, and when the light from an even more distant galaxy passes through that cluster on its way toward Earth, something quietly extraordinary happens. The light is bent, scattered, refracted, as though passing through a lens made of pure gravity. The distant galaxy's image becomes distorted. It stretches, it multiplies. Where you should see one object, you see multiple images, or arcs of light, or Einstein rings, perfect circles born from alignment and invisibility. The beauty of this phenomenon lies in its restraint. It is not violent, it is not sudden. It is simply the patient expression of mass warping the space around it. And unlike every other method we have for detecting dark matter, which require particle detectors deep underground or statistical arguments about galaxy rotation, gravitational lensing shows you directly where the dark matter must be. You can map it. You can trace the invisible scaffolding by watching how the light bends around it. The mathematics allows you to reverse engineer the location and quantity of the unseen mass from the degree and pattern of the bending. Think of it this way. If you were in a forest at twilight, and you could not see a large boulder directly, but you could see how a stream of water curved and split as it passed nearby, you would know the boulder was there. You would know its approximate shape and size from the behavior of the water alone. Gravitational lensing is the cosmic equivalent of this quiet deduction. The water is starlight, the boulder is invisible mass, and the forest is the universe itself, patient and full of such gentle revelations. There is something almost restful about the concept. The universe is constantly performing these delicate bending acts. Light from the earliest galaxies, light that has traveled for 13 billion years through the dark, is being gently deflected by massive structures it encounters. These invisible gravatures act like ancient lenses, focusing and magnifying the distant past for us. Without them, we would see far less of the early universe. With them, we glimpse deeper and more clearly. It is as though the dark matter itself is helping us to see, by bending the light toward our eyes. Cosmologists and observational astronomers spend thousands of hours mapping these lensing effects across the sky. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope stare at distant galaxy clusters and catalogue the warped, distorted shapes of the galaxies behind them. From these distortions, a picture emerges. The dark matter is not uniformly distributed. It clumps. It gathers around visible matter like an attentive shadow. It forms filaments and walls, an invisible architecture that holds the visible universe in place. The calculations required to reverse the lensing effect, to figure out where and how much dark matter must be present to produce the observed bending pattern, are elegant but demanding. And yet the results are consistent. Whether you use lensing data or rotation curves from spinning galaxies or measurements of the cosmic microwave background, the conclusion is the same. Dark matter is real, it is abundant, it is everywhere, and it is bending light on its quiet, patient way through space. There is a meditative quality to contemplating this. Light itself, that fastest, most insistent phenomenon we know, is being gently redirected by mass you cannot see, in ways you would never detect unless you looked very carefully. The universe is full of such invisible gestures. Mass is curved, space is bent, light obeys, and from these patient, obedient paths through warped space, we deduce the presence of something that comprises nearly a quarter of all that exists. There exists in the universe a moment of cosmic collision that has become, in its way, one of the most serene pieces of evidence we possess. Some 8 billion years in the past, two enormous clusters of galaxies drifted toward each other through the vast silence of space, drawn by gravity's patient pull. The Bullet Cluster, as it came to be called, represents perhaps the gentlest proof that dark matter is not merely a theoretical comfort or a mathematical placeholder, but something genuinely, physically separate from the ordinary matter we can see. And the way we discovered this separation has all the quality of watching two streams meet and part, each flowing along its own invisible current. For centuries, physicists had wondered whether dark matter was simply ordinary matter that had somehow hidden itself from our telescopes, thick clouds of cold gas perhaps, or countless small brown dwarfs too faint to detect. Dust and darkness might explain the missing gravity, but the Bullet Cluster showed us something far more profound. When these two galaxy clusters collided, traveling at speeds that would make our fastest spacecraft seem perfectly still, they encountered each other with tremendous force. The visible matter, the gas, the stars, the light-emitting hydrogen and helium, interacted directly. Atoms collided with atoms. Energy radiated outward as X-rays. It was, in the cosmic sense, a tumultuous, visible event. The collision created a shock wave that burned through the intercluster medium, slowing the ordinary matter considerably, piling it up like a tremendous knot where the two clusters had met. But something extraordinary happened to the dark matter, unimpeded, unfettered. The dark matter of each cluster simply passed through, as if the other's dark matter barely existed, exerting only the gentlest gravitational influence. Two invisible rivers flowing past each other, barely touching. The visible wreckage, the tangled gas, the heated plasma, remained behind at the point of collision, creating a visible scar of X-ray emission. But the dark matter, invisible and untouched, drifted calmly onward, continuing its journey through space as though the collision had been merely a whisper. This separation between the visible debris and the invisible scaffolding became the smoking gun, so to speak, though the smoke and the gun were in entirely different places. When astronomers observed the bullet cluster using a combination of X-ray telescopes and gravitational lensing measurements, they discovered something that had profound implications for our understanding of what dark matter actually is. The gravitational lensing, that gentle bending of starlight by invisible mass, revealed that the center of gravity for each cluster lay displaced from the visible gas. The dark matter had indeed moved past the collision point, while the ordinary matter had stayed behind, slowed by friction and electromagnetic forces. It was as if you had thrown two transparent boxes full of invisible sand at each other and watched the sand pass through while the boxes stuck together. The spatial separation proved that dark matter and ordinary matter were distinct entities, not the same thing hiding in darkness. This finding was particularly gentle in its way because it did not require dark matter to possess any exotic properties beyond what we already suspected. It did not need to be alive or conscious or capable of choice. It simply needed to be what it appeared to be, matter that interacts gravitationally but not electromagnetically, that casts gravitational shadows but no visible light. The bullet cluster simply allowed us to see, or rather to measure indirectly, that such matter truly existed in the quantities we had predicted. It was confirmation arriving across 8 billion years of space, a quiet affirmation of what patient observation had begun to suggest. Consider the mathematical elegance of what was discovered. Using gravitational lensing, that subtle warping of space around massive objects, researchers could map where the mass actually was, whether visible or invisible. They could see the X-ray glow of the collision's wreckage in the center, but when they looked at where gravity was actually pulling on the light from distant galaxies, they found the gravitational center of mass was offset from the visible gas. The dark matter, measured through its gravitational effects alone, had drifted onward. This was not theoretical speculation. This was direct observational evidence of spatial separation. The universe had written its answer across billions of light years, and all we had to do was learn to read it. The significance of this discovery rippled gently through cosmology and physics. For decades, some theorists had proposed alternative theories of gravity, modifications to Einstein's equations that might explain the missing mass without requiring dark matter at all. But if gravity were fundamentally different, these alternatives predicted that the gravitational center of mass should align with the visible matter. The center of gravity should lie where the X-rays were brightest, where the collision had occurred, where the ordinary matter had piled up. Instead, the gravitational evidence showed the mass was offset. This was precisely what we would expect if dark matter were real and separate. The bullet cluster was, in a way, a cosmic jury, rendering a verdict after billions of years of deliberation. There is something deeply soothing about this knowledge, the way it unfolded, the patience with which the universe revealed its secrets. No dramatic breakthrough happened in a laboratory. No theoretical flash of insight suddenly illuminated the darkness. Instead, Astronomers simply observed what was already there, waiting in the sky. Two clusters had collided billions of years ago, and their collision had created a natural experiment of staggering scale. We were simply fortunate enough to be here now, with telescopes sensitive enough to read the results. The Bullet cluster drifted on through space, its two components, visible and invisible, now slightly separated, like dancers who had passed through each other in an elaborate cosmic waltz, each continuing along its own trajectory. And so we arrive at perhaps the most intimate question that physicists have been asking themselves in the quiet hours of their work. What actually is this dark matter? What particle, what presence, what ghost of the universe might constitute the very foundation upon which galaxies rest? The answer, if we are honest with ourselves, is that we do not quite know, and there is something deeply peaceful about that admission. Science, at its best, does not demand certainty the way everyday life does. It tolerates mystery with remarkable grace. It sits with questions the way a patient gardener sits with soil, waiting for something to grow. Among the leading candidates for what dark matter might be, there exists a family of particles with names that sound almost poetic in their reserve: WIMPs. Weakly interacting massive particles. There is something almost tender about that acronym, isn't there? A WIMP would be a particle so subtle, so reluctant to engage with ordinary matter, that billions of them could pass through your body in a single second, and you would feel absolutely nothing. They would drift through the earth as if the planet were barely there. They would slip through stone and bone and blood without leaving a trace, guided only by the patient gravity they exert on everything around them. The beauty of the WIMP hypothesis lies in its modesty. These particles would not need to be enormous or heavy by the standards of particle physics. They would simply need to be massive enough, numerous enough, and distributed widely enough throughout space that their collective gravity could account for all the missing mass we observe in galaxies. Physicists have calculated what their properties might be, and they have built elaborate underground experiments to try to catch one in the act of passing through. Imagine that, sitting in silence, deep beneath the earth, waiting for a single WIMP to collide with an atomic nucleus once every few years. There is a kind of monastic dedication in that pursuit. But WIMPs are not alone in the conversation. There exists another candidate, even more elusive if such a thing is possible, called the axion. The axion is almost absurdly small. It was proposed originally to solve a different puzzle in particle physics, but it turns out that axions might also do very well as dark matter. An axion would be so tiny, so feather-light, that even smaller than a WIMP it would drift through the cosmos in clouds of unimaginable density. If dark matter were indeed composed of axions, then the universe would be filled with a gentle rain of particles so fine that they would be utterly imperceptible to our current instruments. Yet their gravity would still bend light. Their presence would still shape the very structure of galaxies. There is something almost meditative about contemplating this possibility. What if the scaffold of the universe were made not of anything we could ever touch or see directly, but of particles so minute, so numerous, so calm in their wanderings, that they existed in a realm altogether separate from our sensory experience? We would only ever know them through their gravitational effects, the way one might know the wind only by watching how it moves the trees. Beyond these primary candidates, there exist other theories, whispered about in seminars and published in journals read by perhaps 100 people in the world. Sterile neutrinos, for instance. Neutrinos that are even more ghostly than their standard cousins, passing through matter with such reluctance that they would interact with nothing at all except gravity itself. Dark photons, primordial black holes formed in the very early universe, small enough to float through space like cosmic debris. Each of these ideas has its own modest following of researchers. Each carries its own elegant mathematics. and each represents a kind of intellectual gentleness, a willingness to explore possibilities without demanding immediate proof. What is remarkable about all of these candidates is how they share a certain quality. They are all, in a sense, invisible by nature. They do not hide simply because they are far away, or small, or obscured by dust. They hide because their fundamental interactions with ordinary matter are extraordinarily weak. They are not dark because something is preventing us from seeing them. They are dark because darkness is, in a very real sense, their natural state. This seems like an important distinction to hold on to as we move deeper into this story. Dark matter is not a failure of observation. It is not something we have simply overlooked. It is something genuinely difficult to detect because it lives in a realm of physics that our most sensitive instruments can barely touch. And so physicists have built laboratories far underground, away from the cosmic radiation that blankets the surface of the Earth. In these silent chambers, kept cold and still, and shielded from disturbance, they have assembled delicate detectors waiting for that infinitesimal moment when a WIMP or an axion or some other candidate particle might reveal itself. These experiments often run for years, collecting data in the quiet and finding nothing. Yet nothing, in this context, is itself meaningful. Each negative result narrows the possible properties of dark matter, like a sculptor slowly revealing a form by removing everything that is not essential. There is a restful quality to this kind of patience, to this willingness to sit in the dark and wait for a signal that may or may not come in your lifetime. It speaks to something fundamental about the scientific process, that we do not always demand immediate answers, that we can sit with uncertainty and still find it beautiful. The particle that constitutes dark matter has been waiting for billions of years to be discovered. It can wait a little longer. Deep beneath the Earth, in places chosen for their profound quietness, scientists have built laboratories where they wait. Not for anything we can see or touch or easily understand, but for the whisper of dark matter itself, a single particle perhaps, drifting through the rock and stone like a ghost through a wall, leaving behind only the faintest of signals if it collides with ordinary matter at all. These underground sanctuaries exist because the universe is noisy. At the surface of the planet, cosmic rays fall constantly, their showers of particles making it nearly impossible to detect the subtle knock of a dark matter candidate. So physicists have learned to dig deeper, to tunnel away from the interference of the sky itself, seeking silence where mystery might announce itself in a whisper. The Gran Sasso Laboratory in Italy sits beneath nearly a mile of mountain stone. The Lux experiment, which ran in South Dakota, occupied a chamber deep in the Homestake gold mine, in rock that had been cooling undisturbed for billions of years. The Xenon collaboration, working in a tunnel beneath the Italian Alps, deployed tanks of liquid xenon, a noble gas so sensitive that it could theoretically register the collision of a dark matter particle with its atoms, producing a tiny flash of light that only the most patient detectors could perceive. Each of these places embodies a particular kind of scientific patience, a willingness to wait and listen in the dark for something that may never come or that may take years of vigilant observation to arrive. Imagine the sensory landscape of such a laboratory. Constant, stable temperature, the hum of cryogenic systems maintaining xenon at nearly 165 degrees below 0 Celsius, the electromagnetic hum of sensitive photodetectors waiting, perpetually alert but calm, the physical weight of the mountain above pressing down with the same steady force it has exerted for eons. In this environment, a scientist might work a night shift, monitoring data streams, watching for anomalies, for that one event in millions that might be different, might be the signal. Most nights yield nothing, most months yield nothing, most careers spent in dark matter detection yield years of null results, and yet the work continues with remarkable serenity. There is something profoundly peaceful about this kind of waiting, isn't there? The knowledge that you are searching for something that will, almost certainly, elude you, and yet the search itself is the point. The question becomes not, will we find it tonight? But rather, what will the absence of a signal teach us? Each negative result narrows the possibilities, constrains the mass and interaction strength that dark matter particles could possess. The universe, in its silence, slowly reveals the boundaries of what is possible. The Super CDMS experiment, also deep underground in the Sudan mine in Minnesota, took a different approach. Rather than liquid xenon, it used cold crystals, silicon and germanium cooled to near absolute zero, watching for the gentle recoil of atomic nuclei when struck by passing dark matter. At such low temperatures, even the thermal vibrations of atoms are suppressed to near stillness, making the laboratory almost eerily quiet, not just in the acoustic sense but in the quantum sense. The noise floor drops so low that when it does register an event, distinguishing signal from background becomes an intricate dance of analysis and restraint. What sustains the people who do this work? Perhaps it is the meditation of it, the repetitive, careful observation, the slow accumulation of knowledge, even when no discovery is made. A physicist spending a week underground, monitoring equipment that will almost certainly detect nothing unusual, has nevertheless participated in something vast, a global network of laboratories spanning continents, all coordinated in their collective silence, all listening in unison for the same elusive whisper. When one experiment reports a potential signal, it may take months or years to determine whether it is real or a false echo born from instrumental quirk. But the conversation between experiments is patient, thorough, and gentle. Some of the most sensitive experiments have placed detectors not just in mines on Earth, but in deep underwater caverns, beneath thousands of meters of water that shield them from cosmic radiation. The Antares Neutrino Telescope sits on the Mediterranean seafloor, its photomultiplier tubes facing upward toward the faint light that might be produced by a dark matter annihilation event. There is something almost dreamlike about the image, these sentinel detectors resting on the ocean floor in eternal darkness, waiting for a signal that may take years or decades or never to arrive. The researchers themselves speak of their work with a kind of calm acceptance. They know that dark matter detection, when and if it comes, will be subtle. A few excess events above the expected background. A signal that builds slowly over time. Not a dramatic flash or a sudden revelation, but a gradual recognition that something real, something hidden from us for so long, has finally touched human instrumentation. And until that moment, if it comes, they maintain their vigil. They tend their equipment, they analyze their data, they meet in conference rooms to discuss possibilities, and they return to the quiet laboratories beneath the earth to listen once more. Is there comfort in this? Perhaps. The acceptance that the universe may guard some of its secrets for a very long time. The knowledge that even failure to detect is itself valuable information. A kind of knowing through negation. The laboratories themselves become places of contemplation, where the boundary between searching and waiting dissolves into something quieter, something more like belonging to the mystery itself rather than standing outside it, demanding answers. And in the darkness beneath the earth, in the steady hum of instruments and the eternal cold, the scientists wait, not with impatience or frustration, but with the kind of peaceful persistence that mirrors the dark matter itself, invisible and patient and woven through all things. And so we arrive at perhaps the most tender chapter in dark matter's story, not its detection, not its theoretical nature, but its role as the universe's first architect. In the beginning, in those earliest moments after the Big Bang, when the cosmos was still hot and dense and utterly unformed, Dark matter was already there, already working. It did not flash or radiate. It did not announce itself. It simply began, very gently, to pull. Picture, if you will, the infant universe about 380,000 years after the Big Bang. The light had just begun to separate from matter, a moment we call recombination. The universe was cooling. And in this cooling darkness, tiny fluctuations existed, infinitesimal ripples in the density of dark matter itself, places where the invisible substance had gathered just slightly more thickly than elsewhere. These were the seeds. These were the whispers from which everything would grow. Here is a quieting thought. Dark matter's gravity, in those earliest moments, was pulling ordinary matter, the atoms and particles that would one day become stars and planets, and the vast clouds of gas between them, into the very slight depressions it had created. Ordinary matter, which we might think of as the primary actor in cosmic history, was actually following. It was being cradled. Dark matter was the patient curator, preparing the landscape long before the first stars would ignite. Across hundreds of millions of years, as the universe expanded and cooled further, these small concentrations of dark matter grew ever more pronounced. Gravity amplified them, drawing in more dark matter from the surroundings, deepening the wells. And as these invisible reservoirs deepened, they pulled ordinary matter along with them, clouds of hydrogen and helium, the primordial gases that had filled the universe since the first moments. The ordinary matter, falling into these dark matter wells, began to collapse under its own weight. It began to compress. It began to heat. And in that compression, something beautiful happened. When the ordinary matter grew dense enough and hot enough, when it had been gathered sufficiently by the invisible hands of dark matter, nuclear fusion ignited. The first stars were born. Consider what this means. The first stars, those brilliant pioneer lights that eventually broke the dark ages of the cosmos, emerged not from random chance, but from the careful structure that dark matter had already woven. Dark matter had done the organizing work. Dark matter had prepared the foundations. The visible stars, magnificent as they were, arrived as guests in a home already constructed for them. But the story grows more intricate still. As these early stars clustered together, drawn by the dark matter scaffolding that surrounded them, galaxies began to form, great rotating disks and elliptical clouds of stellar light. Yet here lies a profound mystery that remains soothing in its own way. Galaxies formed much faster, much more readily, than calculations suggested they should have. Without dark matter's gravitational well to hold them together, to keep the ordinary matter from dissipating back into the void, there would have been no galaxies at all. The gravitational binding energy provided by dark matter allowed galaxies to cohere. It allowed them to persist. In the modern universe, this relationship continues in a kind of invisible dance. Observe a spiral galaxy, one of those elegant, rotating disks of starlight we admire in telescopes. The very structure of that disk, the orderly way in which stars orbit the galactic center, is sustained by the dark matter halo that envelops it. The dark matter surrounds and permeates the galaxy, providing the bulk of the gravitational force that keeps the whole structure bound together. Without this invisible envelope, the galaxy would fly apart. The outer stars would drift away into the cosmic void. Might we say, then, that visible galaxies are embedded within dark matter, rather than the reverse? That seems a fair reframing. Each galaxy we see is rather like a jewel mounted in an invisible setting, the setting being far more massive than the jewel itself, yet revealing itself only through its gravitational influence. This is not a troubling thought, but rather a comforting one. The universe, at its largest scales, is held together by an abundance of invisible structure. Mystery and order are woven together. Computer simulations, run by cosmologists over the past few decades, have allowed us to watch this process unfold in mathematical miniature. Scientists begin with the initial conditions just after the Big Bang, tiny fluctuations in the dark matter density field, extracted from observations of the cosmic microwave background. Then they allow the laws of gravity and the expansion of space to operate, watching as the dark matter clumps and filaments grow as the cosmic web assembles itself. And then, in these simulations, they let ordinary matter fall into the dark matter's gravitational wells and form stars and galaxies. What emerges is remarkable. These simulated universes begin to look like our own. They produce galaxies of the right sizes, in the right quantities, arranged in the right patterns. The great voids and superclusters that characterize the large-scale structure of our cosmos, these emerge naturally from dark matter's influence. Without dark matter, without its dominant gravity shaping the cosmic web, the simulated universe looks nothing like reality. There is a particular passage in the dark matter story that deserves a moment of reflection. When we say that dark matter cradled the first stars, we are not using merely poetic language. We are describing a physical reality. The gravitational potential wells created by dark matter concentrations provided the environments in which ordinary matter could cool, collect, and ignite. In this sense, every star in every galaxy owes its existence to dark matter's patient, invisible work. And the galaxies themselves, the spiral patterns we admire, the great elliptical aggregates, the dwarf galaxies that populate the cosmic suburbs, each of these gained its shape and structure from the dark matter scaffolding within and around it. A galaxy's rotation, its stability, its ability to maintain coherence through billions of years of cosmic history, all of these depend fundamentally on dark matter's presence. Remove the dark matter from a galaxy, even in imagination, and the galaxy becomes something entirely different. The visible stars would no longer have the gravitational anchor they require. The whole system would come apart. In our own Milky Way, we are surrounded by this invisible structure. We live within a dark matter halo, a vast, spherical distribution of invisible particles extending far beyond the visible disk of our galaxy. This halo keeps our galaxy bound together. It provides the gravitational force that maintains our solar system's orbit around the galactic center. In a very real sense, dark matter is responsible for our continued existence as stable structures orbiting a stable star in a stable galaxy. There is something profoundly calming about this realization. We are not isolated points of light floating alone in a void. We are embedded within a vast network of structure, visible and invisible. We are held in place by forces we cannot see, by a substance we do not fully understand, but whose existence is as undeniable as gravity itself. The universe is not fragmented and chaotic at its largest scales. It is organized. It is connected. It is bound together by an intricate tapestry of dark matter, the greatest architect of structure the cosmos has ever known. As our understanding of dark matter deepened through those patient decades of observation, a new kind of tool began to emerge in the latter part of the 20th century and into our own era. These were not ground-based telescopes peering upward into the night, but satellites drifting quietly in the vacuum above us, each one carrying instruments sensitive enough to read the subtle whispers written across the cosmic microwave background, that ancient light that has been traveling through space for nearly 13.5 billion years. The Planck satellite, launched in 2009, became one of the most patient mapmakers the universe has ever known. Imagine an instrument so sensitive that it could detect temperature variations smaller than millionths of a degree across the entire sky, and you begin to approach what Planck accomplished. As it orbited at a point called Lagrange 2, far beyond the moon's distance, it was quietly reconstructing the infant universe, not through direct vision, but through the faint afterglow of the Big Bang itself. Every cold spot and warm spot in that ancient radiation carried within it the fingerprints of dark matter, the invisible scaffolding that shaped how matter clumped and gathered in those first moments after creation. What makes this work so restful to contemplate is its sheer patience. The satellite didn't rush. It swept across the sky again and again, gathering photons, building maps with such precision that scientists could tease out how much dark matter existed at different distances from us, how it was distributed, how it had evolved over cosmic time. The data it returned didn't come in flash and revelation, but in steady streams, year after year, each measurement a small tile in an enormous mosaic of understanding. And then there is Gaia, a different kind of sentinel altogether. Launched by the European Space Agency in 2013, Gaia began its work of mapping the positions, distances, and motions of nearly 2 billion individual stars in our own galaxy, the Milky Way. This might seem, at first thought, to have little to do with dark matter. After all, these are visible stars, burning bright. Yet Gaia's work has become something far more subtle and profound. By precisely charting where each star is and how it moves through space, astronomers can deduce the gravitational pull acting on it. And gravity, as we know, comes from all matter, both the visible and the invisible. The starlight follows paths curved and guided by dark matter that Gaia itself cannot see, but whose presence it reveals through the mathematics of motion. The sheer scale of this map-making effort is worth pausing to consider. Gaia measures the positions of stars not in mere degrees or minutes of arc, but in micro-arc seconds. Imagine dividing the width of a human hair as seen from 20 kilometers away into smaller and smaller fragments. This is the realm in which Gaia works, and in this realm, the subtle gravitational influences of dark matter become apparent. Streams of stars disrupted by the approach of invisible structures, patterns of motion that only make sense if there is far more mass in our galaxy than we can see shining before us. Gaia has revealed that our galaxy is not a serene, unchanging place, but a dynamic realm where the dance of visible and invisible continues, ancient and ongoing. Both of these satellites, along with others, have begun to paint a portrait of the universe that blends precision with mystery. The cosmic microwave background maps from Planck have refined our understanding of the universe's composition with stunning accuracy. That 27% of the universe we spoke of earlier, the fraction that appears to be dark matter, that number comes from the careful work of missions like Planck, combined with observations from ground-based surveys that have mapped the distribution of galaxies across billions of light-years. These surveys, vast compilations like the Sloan Digital Sky Survey and now the Dark Energy Survey sweeping across the southern hemisphere, have traced the cosmic web with increasing clarity. They have shown us where dark matter accumulates, how it clusters and flows, how it shapes the architecture of everything we see. What is particularly soothing about these modern surveys is how they have transformed dark matter from something that felt abstract and almost philosophical into something measurable and mapped. It is no longer merely a mysterious invocation to explain why galaxies spin too fast. It is now part of a vast, intricate landscape that we can point to and measure. We can say, in this region of space, there is dark matter here, and here, and here. We can watch its influence ripple through time as the universe aged. We can see how its distribution shaped the first galaxies and continues to shape them still. The work is ongoing, of course. Future surveys will only sharpen the picture. The James Webb Space Telescope is peering back through time itself, seeing galaxies as they were in the universe's youth, allowing us to watch dark matter at work in the earliest epochs of creation. Ground-based observatories are developing increasingly sophisticated ways to detect the faint signals of gravitational lensing, watching how clusters of dark matter gently bend the light of distant galaxies as that light passes through them. Each new observation adds another layer to our understanding, another quiet confirmation that this invisible substance is woven throughout the cosmos, patient and present. And perhaps this is what makes the modern era of dark matter research so restful to contemplate. We are no longer simply wondering. We are measuring, we are mapping, we are gathering evidence with machines that never tire, that work night and day in the quiet of space, slowly, methodically filling in the details of the universe's greatest mystery. The uncertainty has not vanished. It has only deepened and grown more textured. But there is something deeply soothing about knowing that scientists and instruments are devoted to this patient work, systematically learning the shape of the invisible, one measurement at a time, letting the universe reveal its secrets at its own unhurried pace. Yet even as the evidence for dark matter grew deeper and more elegant, a question lingered in the minds of some thoughtful physicists. A question as quiet and persistent as wind through an empty hall. What if, they wondered, we were looking at the problem through the wrong lens entirely? What if the galaxies were not being pulled by some invisible substance, but rather the laws of gravity themselves were different from what we believed on the grandest scales? This gentler path of thinking emerged in the 1980s, when a physicist named Mordechai Milgram sat with his equations and asked a deceptively simple thing. Instead of adding dark matter to the universe, why not adjust our understanding of how gravity behaves at very large distances? He proposed what became known as modified Newtonian dynamics, or MOND, and in that proposal lay a kind of aesthetic appeal, the universe operating not by hidden things, but by hidden rules. In MOND's framework, gravity doesn't behave quite as Newton described it on cosmic scales. At the enormous distances between stars within a galaxy, or between clusters of galaxies, gravity becomes subtly stronger than our traditional equations would predict. No invisible mass needed, no particles never yet detected, just a gentle reshaping of the fundamental law itself. It's a hypothesis that carries a certain elegance, doesn't it? A universe that asks us to revise what we thought we knew, rather than populate itself with something we cannot touch. Think of it as a scientist gently suggesting that a shadow on a wall might not be cast by something hidden behind it, but rather the wall itself might be shaped differently than we assumed. The shadow remains real, the problem remains, but the solution changes entirely. For a time, MOND and its various extensions offered genuine explanations for many of the observations that seemed to require dark matter. Rotating galaxies moved at their puzzling constant speeds without needing invisible halos. The way galaxies clustered together followed patterns that MOND could accommodate. There was something almost restful in the simplicity of it. Fewer entities in the universe, fewer mysteries piled upon mysteries. The principle of parsimony, that old and soothing rule of science that tells us simpler explanations are often truer, seemed to lean in MOND's direction. Yet as measurements became finer and instruments grew more sensitive, the picture grew more complex. MOND explained some observations beautifully while struggling with others. It worked wonderfully for galaxies, for the rotation curves and the clustering. But when cosmologists looked back in time, when they examined the light from the earliest universe and the structure imprinted on the cosmic microwave background radiation, dark matter seemed far more necessary. The ancient light bore patterns that MOND could not easily explain. The way galaxies had formed in the first billion years of cosmic history seemed to require dark matter's presence, its gravitational scaffolding cradling the first stars like invisible hands. And yet scientists who work with modified gravity theories have not ceased their work. They continue to refine their ideas, to explore variations, to test whether some hybrid approach, combining modified gravity with a smaller amount of dark matter, might capture more of the truth. There is something beautiful about this persistence, this refusal to abandon an elegant idea simply because it has grown difficult. Science, at its most generous, maintains multiple working hypotheses, allowing them to exist in a kind of productive tension until evidence finally tips the scales one way or another. There are other alternative frameworks too, each approaching the mystery from a different direction. Some physicists have wondered whether the laws of gravity themselves might vary depending on the strength of the gravitational field. What if gravity behaves one way in regions of intense warping and another way in the gentler fields between galaxies? Others have asked whether we might be misunderstanding the relationship between matter and space-time at cosmic scales, whether the geometry of the universe itself might respond to its contents in ways we have not yet fully grasped. These are not wild speculations, though they might sound so to an untrained ear. They are serious scientific investigations conducted by careful researchers who understand both the power and the limitations of the Standard Model. They represent what we might call honest uncertainty, the recognition that our current framework, for all its impressive successes, might not tell the complete story. What makes these alternative pathways so soothing to consider, perhaps, is that they remind us that science is not a finished cathedral, not a completed puzzle. It is more like a slow, patient conversation with the universe itself, a back and forth that continues indefinitely. We propose, the universe answers. We listen, we refine, we propose again. None of us knows where this conversation will ultimately lead. It's possible that dark matter is exactly what we think it is, some yet undiscovered particle that barely interacts with ordinary matter, drifting through galaxies in vast halos, invisible and fundamental. It's possible that some form of modified gravity holds part of the answer. It's possible that the truth is something we have not yet imagined, some entirely different way of thinking about the relationship between matter, space, and time. And that uncertainty, that gentleness of not knowing, not needing to know immediately, is perhaps the most restful aspect of all. The universe does not rush. The answers are not going anywhere. Somewhere in underground laboratories tonight, scientists are still listening for signals from hypothetical particles. Somewhere else, others are still working through equations, asking whether gravity might bend the rules. And somewhere in between, the actual truth waits patiently for us to find it, as it has waited for billions of years, indifferent to our searching, peaceful in its silence. And so we arrive at perhaps the most extraordinary and, in its own way, most restful fact of all, that nearly a quarter of everything that exists, 27% of the entire universe, remains invisible to us, interwoven through space, like a vast quiet presence we can feel but cannot see. For decades, this would have been called unsettling, a gap in knowledge, a problem to be solved, but there is something strangely calming about sitting with this reality, about understanding that the greatest mysteries need not be solved to be beautiful. Think of how much of human anxiety comes from the need to know, to name, to control. We fill silence with noise. We fill darkness with light. But dark matter invites us to do something different. It asks us to accept that the universe operates on a scale far grander than our instruments, and that not all truths come to us immediately or wrapped in certainty. In fact, some of the most profound truths seem to wear invisibility like a garment. When Vera Rubin measured those galaxy rotation curves and found them flat and steady, defying what gravity alone could explain, she could have felt frustrated. Instead, what followed was a gentle unfolding. The mystery did not disappear, it deepened, and in deepening, it opened doorways into questions that were far more interesting than simple answers could ever be. What if the universe is not simpler than we think, but infinitely richer. What if we are not meant to see everything, but only to sense its presence and adjust our understanding accordingly? There is rest in that acceptance, rest in knowing that dark matter is not a problem that science has failed to solve, but a patient teacher showing us the limits of our sight. The universe is not broken because we cannot directly observe dark matter. The universe is whole. We are simply learning to perceive more of it with each passing decade. Consider, too, the perspective shift that dark matter offers. For most of human history, we believed that what we could see was all there was. Stars, planets, dust, light. These were the substance of existence. But in the last 90 years, we have discovered that what we can see is the minority. The visible cosmos is like a few bright threads woven into an immense tapestry of which we glimpse only the illuminated portions. And yet somehow this does not make us feel smaller in the universe. It makes us feel more connected to it. If we are made of matter, and matter is shaped and held together by dark matter, then we are touched by the invisible architecture even as we walk beneath the stars. The patience required to study dark matter is itself meditative. In those deep underground laboratories we spoke of earlier, scientists wait in silence, listening for signals that may never come, at least not in their lifetimes. They do not wait anxiously. They wait with the quiet discipline of astronomers waiting for a celestial event, knowing that patience itself is a form of respect. Respect for the vastness of what they are trying to understand. This is not the frantic pace of modern life. This is the tempo of the cosmos, measured in centuries and millennia. And when you reflect on the fact that this invisible substance comprises 85% of all the matter in the universe, that every galaxy we see is actually just the bright, visible fraction of something far more massive and invisible, it becomes easier to relax into the mystery. What else might we not be seeing? What other aspects of reality do we take for granted as complete when they are, in fact, only the visible surface of something infinitely deeper? Dark matter teaches us that wholeness and mystery are not opposites. A system can be complete, balanced, and comprehensible even when it contains elements we cannot directly perceive. The Earth is whole even though we cannot see the magnetic field that protects us. Our bodies are entire even though we do not see the vast colonies of bacteria that make digestion possible. The universe is complete even though we cannot see the dark matter that shapes it. Perhaps this is why dark matter, among all the great unsolved problems of physics, feels oddly soothing to contemplate. Dark energy pushes outward, accelerating the expansion of space itself, and there is something slightly vertiginous about that, something that makes the heart beat a little faster when you truly sit with what it means. Dark matter, by contrast, simply rests. It accumulates gently around galaxies. It holds clusters together with a patient gravity that has operated for billions of years unchanged. It is not dramatic or violent or explosive. It is the quiet backbone of the universe. There is also something restful about problems that do not demand immediate solutions. In our ordinary lives, we are urged toward rapid answers and quick fixes. But the dark matter problem has been with us for nearly a century, and it is likely to be with us for at least another century. And that is all right. There is no shame in a mystery that unfolds slowly. Perhaps there is wisdom in it. What if you allowed yourself for just a moment to release the need for all your own mysteries to be solved? What if some of the things you do not understand about your own life could simply be accepted as part of the larger tapestry, the invisible architecture that holds you in place even though you cannot always see its presence? Scientists working on dark matter often speak of a quality they call elegance in a theory. Not simplicity necessarily, but elegance. A kind of harmony between the observed facts and the explanation. A sense that something is true because it feels right, because it fits, because it solves not just one problem but many problems at once. There is elegance in the idea that the universe is not mostly empty, but mostly full of something we cannot see. There is elegance in knowing that we are surrounded by invisible structure, held in invisible hands, guided by invisible forces into the shapes we inhabit. And that is where we rest now, in the thought that mystery itself is not an obstacle to peace. Mystery is an invitation to humility, and humility, in turn, is an invitation to sleep. And so, as the night deepens around you, imagine for a moment that you are drifting through the very fabric of the universe itself, not through the bright, cheerful points of starlight that have guided human wanderers for millennia, but through the vast, patient darkness that cradles them all. The darkness that asks no questions, makes no demands, simply exists in its overwhelming majority, holding everything in a gentle, invisible embrace that science has only begun to whisper about. Think of yourself suspended in that cosmic dark, moving slowly through filaments of dark matter that stretch across billions of light years, like the quietest architecture ever built. There is no sound here, of course. Space offers no echo, but if there were a sound, it would be something like the slowest sigh, the gentlest breathing of the universe itself as it expands and unfolds through time. All around you, this unseen substance forms a kind of skeleton, a scaffolding so vast and patient that it makes the great cathedrals of Earth seem like hasty sketches drawn in sand. As you drift deeper into this darkness, consider that within these invisible threads, galaxies are being cradled even now. The stars you see when you look up on a clear night, those brilliant, burning jewels, they exist only because dark matter held their material together in the first moments after the universe began. The dark was there first, waiting. It shaped the light that came after. In a very real sense, you yourself are made of atoms that were collected by this invisible force, gathered into stars and worlds through the patience of something we still do not fully understand. And that carries a certain peace, does it not? To know that you are woven from both the visible and the invisible, held together by mysteries that scientists are still gently untangling in laboratories buried deep beneath the earth. What if mystery itself is meant to be calming? This might seem like an odd notion in a world that prizes certainty and immediate understanding, but there is something profoundly soothing about knowing that the universe still contains secrets. It means there is still wonder left. It means human curiosity will never run dry. The dark matter that makes up most of the universe's mass is not a problem to be solved and discarded, but a constant companion, a reminder that the world is far stranger and more beautiful than we can fully comprehend in any single moment. As you continue your slow drift through the cosmic dark, picture the gentle collision of two galaxy clusters happening somewhere across the vast reaches of space, not violently, as the word collision might suggest, but as a slow-motion dance that takes millions of years to unfold. The visible matter, the brilliant hot gases, collide and slow down, radiating their energy away into space as light and heat. But the dark matter, it drifts calmly past, undisturbed, barely interacting with anything at all, moving through the wreckage like a ghost through a wall. The bullet cluster showed us this truth, and in knowing it, we understand something profound, that much of what holds the universe together is utterly indifferent to collision, to chaos, to the drama that plays out in the visible spectrum. It simply continues, eternally patient. The scientists who search for dark matter particles in their deep underground laboratories, far below the surface where cosmic rays cannot reach them, they are practicing a kind of patient meditation themselves, are they not? Night after night, they wait in silence for perhaps a single signal, a faint whisper of interaction that would confirm the presence of a WIMP or an axion, some particle that barely touches ordinary matter at all. This is not the frantic searching of those who must find answers immediately. This is the slow, methodical observation of those who understand that some truths take time to reveal themselves, and the universe, being under no obligation to rush, has all the time in the world. As your imaginary drift continues, let your thoughts settle like dust through a still room. The cosmic web that astronomers have mapped out, that vast network of dark matter filaments that connect galaxy clusters across unimaginable distances, it creates a kind of order in the chaos. There is structure here, purpose, a slow architecture that has been built over billions of years. Every galaxy you can see is threaded through this invisible structure like beads on an unseen string. The atoms in your body are arranged according to patterns that were set in motion by dark matter's influence. You are not separate from this cosmic order. You are woven into it at the deepest level. And here is something to rest upon as sleep approaches: the existence of dark matter. The mystery that takes up most of the universe's substance reminds us that there is far more to reality than what we can easily perceive. Our eyes, magnificent as they are, see only a tiny sliver of the electromagnetic spectrum. Our instruments have expanded that vision, but even so, we are looking outward from within a bubble of ignorance, able to perceive perhaps 5% of what is actually there. The other 95%, dark matter and dark energy together, remains largely beyond our direct understanding. And rather than being frightening, this can feel like a kind of permission to surrender to the unknown, to let go of the need to understand everything immediately. Think about what Vera Rubin discovered when she patiently studied the rotation curves of galaxies in the 1970s. She noticed something that didn't fit the equations. Rather than assuming the equations must be right and dismissing the observation, she looked deeper, and in doing so, she caught a glimpse of something invisible. This is the spirit of scientific exploration at its most elegant, not the need to have all the answers, but the willingness to follow a gentle mystery wherever it leads, to trust that the universe is telling us something true, even when we don't yet have the language to fully describe it. As you sink deeper into the darkness of the night around you, imagine the light from distant stars bending around a massive concentration of dark matter, their paths gently curved like water flowing around a stone in a quiet stream. Gravitational lensing is one of the few ways we can actually see the effects of dark matter directly. Not the dark matter itself, but its influence, the way it shapes the paths of light itself. There is something meditative in this image, light, that fastest thing in the universe, slowing its path and bending gently around what cannot be seen. It suggests that even the most fundamental forces of nature can be redirected by something unseen, something patient, something that has been there all along. The universe does not need your understanding to continue being the universe. It will expand and cool and evolve according to laws that operated long before humans evolved to perceive them, and it will continue long after. There is a strange comfort in this fact. You are not responsible for holding the universe together. That work is being done by dark matter, by gravity, by the patient unfolding of physics that requires no observer, no witness, no one to validate it. Your only task right now is to let yourself sink into the safety of that knowledge, to trust that you are held by forces far greater and more patient than you can imagine. In the great cosmic dark, in the invisible scaffolding that structures reality itself, there is no urgency. There is no demand that you understand, solve, or complete anything. There is only the slow, steady presence of something vast and ancient and utterly indifferent to your worries. The dark matter will continue its patient work, whether you are awake or sleeping, whether you are worried or at peace. You can let go of the need to grasp it, to fully comprehend it, to fit it into neat categories in your mind. Let it remain mysterious. Let it remain vast and distant and gentle. As your consciousness begins to drift like a ship through dark waters, imagine that you are moving deeper into the cosmic web itself, passing through the invisible threads that connect all things. Around you, galaxies spin in their slow, patient dance, guided by dark matter that has been there since the universe was young. The warmth of those distant stars still reaches you, but here in the darkness, where dark matter lives, there is no heat, no pressure, no urgency whatsoever. There is only the gentle continuation of existence, the quiet unfolding of time, the slow breath of the universe as it has always been. Let the mystery rest with you now. Let the unknown become a companion rather than a burden. In all the darkness that fills the cosmos, in all the mass that remains unseen and perhaps unseeable, there is a profound peace. The universe does not demand your comprehension. It simply asks that you exist within it, that you allow yourself to be held by forces both visible and invisible, both understood and mysterious. And as that permission settles over you, as the weight of all those invisible threads begins to feel less like confusion and more like an embrace, let yourself drift deeper still into the restful darkness where sleep begins and the day finally releases its hold.